Thanks a lot, Chris, and the center for having me here and the invitation. It's also great to hear that I'm going to have job security for the next foreseeable future. I have to say that it's been great to listen to all the talks, especially just the previous one about the contaminants and these emerging contaminants. I'm actually going to focus a little more on the chemical processes, more specifically the electrochemical processes. I just want to actually acknowledge that despite being in a chemical engineering department, I really got into a lot of these challenges by collaborating with environmental chemists and how we actually got into these problems. Actually, NDMA was the one contaminant that I studied during grad school alongside Lokesh, actually, who's going to be part of the center. And so it's very cool to see that being brought up. And so I'm actually, I guess everybody here is pretty aware of the sort of widespread concern about PFAS over the news, especially in the past couple of years. So I won't go over too much here. I just want to say that I guess everybody's also aware of the recent news that the EPA has made PFAS or has sort of classified them as hazardous materials, especially PFOA and PFAS, and then the sort of very strict regulatory levels on them. So there is this huge concern about remediating or treating these compounds. So, they are in many ways been ubiquitous in our everyday lives. I think there has been this range of consumer products. And the main thing is they're synthetic, so they've been produced chemically over the past decades. And so it's going to be, and I'm going to sort of mention, it's going to be in many ways hard to substitute all of them. And so being able to treat them is actually one very important issue. So right now I'm just going to focus a little bit on the way that my group thinks about PFAS in general, all these sort of water contaminant problems. So whether it's PFAS, nutrients, or heavy metals, these are all sort of challenges that my team and others that are doing chemical processes are targeting. It's really two major challenges often. One, especially for PFAS, is the low concentrations in which they are found in the environment or in different streams. And the second one is the case of persistence. And so often these contaminants are found in very low concentrations, ppb, ppm, sometimes ppt levels. And then they're in the presence of multi-component mixtures. So there's a lot of stuff in the solutions that they are in. And so removing them from these low concentrations in the presence of all these contaminants makes it for a very special physical-chemical challenge. But then it's actually coupled with persistence, and I'm going to try and reemphasize why that is. But then they're challenging species to degrade and transform. And so the more challenging it is to degrade or transform, the more important it is to actually separate them. So the more important is the removal, because there is a correlation between the concentration and the energy or cost of actually transforming things. So what I want to emphasize over and over is that the reaction problem for a lot of these contaminants is actually coupled with the separations. And you can see that from just the energy consumption that actually you can have sort of on the rightmost figure there, in which as you increase the PFAS concentration, it becomes a lot easier to degrade them using physical-chemical methods. And so why is PFAS itself unique from a separations challenge? So it's a surfactant that gives us a lot of its valuable properties. And because it's a surfactant, it has unique properties that makes it hard to separate and then regenerate the adsorbents and things like that. And so, for example, if you use a regular ion exchange or a granulated activated carbon, which are sort of benchmarks for removing PFAS, you often can capture them, but you cannot release or regenerate the media very well. And then depending on the PFAS chain, it becomes very hard to capture it. And so I'm going to show a little bit how changing the hydrophobicity and the properties of the PFAS changes its performance in terms of removing it. The second one is its catalytic and the sort of catalytic resistance, its stable bonds, and the environmental concentrations makes the reaction and the degradation part sort of very difficult as well. And so, let me talk a little bit about the sort of concepts of separation science that plays a role in sort of PFAS remediation, but also contaminant remediation in general. So the goal of separation science, which is removing something from a stream, is actually to demix it. And so in our case, we're trying to demix a very low amount of PFAS from a water stream. And so this is just a little bit the challenges that developing a separation method normally encounters. This is actually the report by the National Academy in Separation Science. And what's actually integral to any method that we're actually trying to develop is actually that interface. So the interface of whether it's a liquid-liquid interface or solid interface, that actually dictates the efficiency of a separation method. And in the case of PFAS, we're also talking about things that have we're targeting specifically things that are differences in size, shape, or chemical functionality. And so I think there was some talk today about membrane separations. I'm going to talk about absorption. They all fall under these sort of target metrics here. And so what my group has been trying to do has been, can we use electrical fields and electrochemical reactions to enable this interfacial selectivity and actually be able to target different types of contaminants. And so the one specific technology that I'm going to talk a lot about in this field of electrochemistry is actually redox-mediated separations. I think there's been different discussions on redox transformations. What we're actually trying to do here is actually create a adsorbent. So an electrode is now going to be our adsorbent. We coat it with a film that has actually specific functionalities that when you actually apply a voltage, you can actually demix selectively one ion over another. And so how to achieve this selectivity is really what a lot of research, my group and others, has been focusing on. And then, so molecular selectivity is the first advantage. And then associated with it, you want a process that actually has low operating costs, low energy, and you're not putting chemicals or pH swings. And so by sort of reversing that voltage, you can actually release and concentrate your contaminant. And so it's sort of easy to say how it operates, but it's actually very hard to achieve. So a lot of it is tuning the selectivity and controlling the potential of that redox unit. So you actually achieve all these metrics to be able to be implemented. And just to sort of say that this is a field that when I was a PhD student, there were some examples that were actually, including myself, my PhD advisor, we sort of gave some examples of how it works, and now it's sort of expanded to various different applications. So you can use it for different types of ions, but also carbon dioxide removal even. So you can use it for the gas phase as well. And so what is the design principle behind creating these specific electrosorbents? It's actually fairly simple. In the first order, you want to actually create a redox film that basically binds the target ion that you want selectively. And then at a molecular level, what you want is you just want the target ion to have a higher binding energy than any competing ion. And so you want to structure material so that you actually have this higher selectivity towards what you want. In our case here, PFAS over other things like chlorides or other types of water contaminants. And then you want to be able to engineer these materials for actual practical processes. And so this is one slide I'm going to sort of show about the molecular design principles. There's a lot of it that goes behind the scenes, but I'll be happy to answer more specific questions behind it. And then just to also give, for the sake of completeness, give a little bit of overview on electrochemical pathways. So there has been electrochemical technology developed both in the separation side, which is this sort of electroabsorption, even you might say electrocoagulation is one pathway for it. And then there's also different types of reactive methods in which you're destroying PFAS. And those have been shown to have very high efficiencies, but there's a lot of engineering behind it. And so I'm not going to go over in detail, but if you want to sort of learn more about it, we actually, my student Anira actually wrote a pretty comprehensive review just focusing on these electrochemical pathways. So I'm going to focus a little bit more at the beginning of my talk on the separation methods here, just because of its importance as well. And so a little bit of a timeline on how I got into PFAS. So I actually joined Illinois in 2019, and one of the long-standing desires that I had was collaborating with the civil and environmental engineering community there. And so my collaborators, UJ and Roland, actually brought up PFAS as a challenge to me very early on. And we applied it in 2019, back when I didn't know what PFAS was, what it about. And that was actually definitely a very good investment. And so I'm going to talk a little bit about the work that I did with those guys for the long chain PFAS. But then once that paper came out, actually, I sort of noticed that Lisa had some slides on the 3M. 3M actually produces PFAS by electrochemical fluorination. And so they were very interested in electrochemical defluorination at the same time. And so we had a partnership with them, but they said they were not interested in long-chain PFAS. They were interested in short-chain PFAS. And that's a much tougher challenge from the separations perspective. And then more recently, through the NSF, together with the plasma folks at Illinois, we're interested in the sort of combination of plasma and electrochemical separation. So I'm going to touch a little bit on all these topics, and then just make sure that I'm not going over time here. And so I'm just going to jump into the first challenge. So back in 2019, 2020, PFOA was really the representative molecule that we all wanted to separate. And in PFOA, now, like looking back, PFOA is actually ubiquitous, but it's actually in some ways not the most challenging molecule because it's characterized by its hydrophobicity. So it has a long chain that gives us quite a little bit of hydrophobicity. But then if you sort of look at it, it also has this carboxylic head that is usually charged in water. And so it's a charged hydrophobic molecule. And so when we were looking for adsorbents for it, it was hard to actually balance a adsorbent that could bind it a lot by hydrophobicity, but also be able to release it at the same time. And so electrochemically, to be able to achieve that, you have to be able to turn on and off electrostatics, but also at the same time control the hydrophobicity. And using a single polymer coating, at least in the very beginning when we were searching for it, was not possible. So the solution that we had, which was sort of the genesis of this paper, was can we actually create copolymers in which one group controls a little bit the affinity and the hydrophobicity, and the other group controls electrostatic interactions. And so this polymer here is a tempo polymer. For those that do batteries, it's a very common redox flow battery. And so by oxidizing the tempo, you can actually control its electrostatics. So that nitroxide group in blue controls you can actually make it positively charged to capture the carboxylic, but then the affinity group on the side also regulates a lot of the properties of the polymer in terms of its affinity towards long-chain PFAS. And so what we found here, and then this is, so I'm just going to focus here a little bit on the figure in the middle here. It's an adsorption of PFOA per gram adsorbent, which is a metric of how much can our electrode uptake. And so as the percentage on the top is how much do you have of the blue component of the polymer. And so as you increase the copolymer unit that actually gives us the electrostatic interactions, you start increasing the amount that you can regenerate electrochemically of the PFOA, but you actually take a hit in terms of adsorption. And so these two units actually do different things. One actually enables you to control the electrostatics and then do adsorption, desorption electrochemically, whereas the other one controls affinity. And so you can sort of optimize the percentage of this copolymer to then allow you to actually achieve very high removal efficiencies of PFOA from different solutions. And also, we can also screen other sort of long-chain PFAS and can get pretty good adsorption uptake. And so something that we also were interested in a little bit was actually the removal efficiency of some of the sort of Gen X fluorotelomers. And so the same electrode, the same sort of coated electrode can actually give you pretty good removal efficiencies also for Gen X and other types of fluorotelomers. And there's definitely a little bit of a pH effect because as you sort of protonate the PFAS, you have different affinity sort of interactions. And then I'll be happy to chat a little bit more about it. So one problem that we had with the original polymers as we were developing it was that our regeneration efficiency was not very high. So as you could sort of see for those tempo amine copolymers, you could adsorb a lot of the PFAS, but when you regenerate it, you could only regenerate on 40 or 50% of it. Even though it's steady working capacity, you're also sort of losing a bunch of the adsorption sites. And so one of the ideas that we had was actually, can you control within one monomer unit the electronic structure of your polymer so that you can actually improve the regeneration efficiency. And this actually can be done using this class of metallopolymers, so you can control the redox potential and also the electronic affinity of these this sort of series of metallopolymers, so you can actually start optimizing. So cobalt metallopolymers were shown to actually adsorb a fair amount of PFOA, and then you're able to regenerate 80% steadily in terms of over multiple cycles. So that's one of the advances that my student Paula did as she was working on this sort of long-chain PFAS studies. And so, coming back a little bit towards what do you do once you regenerate the PFAS? You actually want to be able to destroy it. And so the idea that my postdoc Xiao and Paula had was you're using your electrode as a anode when binding the PFAS because it's negatively charged. And then when you release it, you're basically releasing it cathodically, so you're flipping the potential. So now you have this PFOA concentrated in solution. How can you sort of take advantage of the electrochemical couple to destroy it? And so we basically just combined it with a boron-doped diamond electrode, so that's a pretty standard sort of electrocatalytic electrode that's used for different applications. And then we leave it for a few hours, and then you can see that you can actually get a pretty high defluorination efficiency, up to like 80% of the PFOA that's actually being released as well. So you can use one electrochemical cell in which one electrode is being it's adsorbing the PFAS, and then the counter electrode is now defluorinating it. So you're doing two things at the same time. You're concentrating it, you're moving, concentrating, and then you're also destroying it. And so that's a little bit the concept behind combining sort of reactions and separations in one electrochemical cell. And so we can do the same thing for Gen X. What we found with Gen X, though, it was a lot harder to defluorinate it. I think that that's something that would be a question for the environmental chemists, why you have different defluorination efficiencies. But then the other thing we noticed, and I'm going to show a little bit later, is PFOA is actually probably our best case candidate for defluorination. All the other ones, fluorotelomers, shorter chain PFAS, it just takes longer, and we don't know right now if it's a mixture of mass transfer limitations because it's not going to the interface, or is it like a fundamental chemical property? That's an open question, at least to us right now. And so just to show a little bit what the architecture looks of this flow cells, electrochemical systems, is you can run them continuously, and so you can create a flow cell that's basically just two, like sort of either planar or flow through electrodes, and you can track the PFAS uptake and then its release sort of semi-in situ by sort of sampling it, and you can sort of couple these with different types of reaction processes downstream if you need to. And so actually, let me just talk a little bit about the reaction part of PFAS with electrochemical methods. And so, I've been talking a lot about the boron-doped diamond, and then when sort of 3M came to us, they sort of asked a little bit of a question of like, what's the best electrified method for destroying PFAS? And the two that we sort of identified was we can take these boron-doped diamonds, or you can take your favorite catalyst that's electrochemical, and you can see how much it defluorinates. And then there was another technology that's basically plasma technologies that have been also, there's been a lot of work, and then there's been a lot of scale up. And then there's been an argument there, and they both like sort of electrochemical systems. And so there's been argument there whether plasma is better or boron-doped diamond electrochemical methods is better. And your first impression, at least my first impression as an electrochemist was, well, plasma takes a lot of energy because you're generating a plasma, except the current is not that high. And so we took a look actually at a side-by-side comparison together with my collaborator in the nuclear plasma technology. And when we went to literature, and there was a lot of papers saying, well, BDD is better, plasma is better, we noticed that they weren't normalizing their studies based on the same surface area, based on the same sort of PFOA concentrations. And so we actually created a special cell in which most of the conditions in terms of current and voltage and then like surface area were sort of normalized in the way that you can actually compare between the two of them. And the results in some ways are actually not surprising for chemical engineers at least, is that in terms of overall efficiency of PFOA degradation per energy, they're actually quite similar. And the reason for that is because most often, both systems are somehow limited in a way that at the very end of the day, you basically use the same amount of energy. So plasma, because of its high energy and very quick reaction, is actually transport limited for PFOA. And so you actually have to, for the concentrations in which they're occurring, it actually takes a lot of energy to run it, but then you're not running it at the maximum efficiency, and BDD was actually kinetically limited. And so for each of these systems, you actually have to sort of understand what is actually limiting you on it to actually be able to improve them. But sort of the comparison, which one is better, is sort of up for debate, because from our screening, they basically had the same efficiency in general. And then we're right about in the middle of what literature has been reporting as well. And so The punchline that I want to say in this case is sort of the same one that naturally occurs for many chemical processes, is that the reaction step, as long as you go over a sort of thermodynamic or a certain barrier, it's actually a problem not of reaction, but one of separation. So can you actually concentrate the PFAS enough that you can actually have an overall energy efficient system? And so I'm going to move on back to the sort of affinity development of affinity adsorbents and talk about our current biggest challenge, which is short chain. And so when, this is sort of the project with 3M here, is they were very interested in can we actually bind and release PFBA in a way that's efficient? And I have to say that that's actually very tough because we went back to all the electrodes that we've done for PFOA, and very few of them actually, so none of them actually work for PFBA binding and release, just because it's actually it's a pretty hydrophilic PFAS. And then, I'm going to show these, and right now what we're very interested is like even lower, like ultra short PFAS, and those you're basically dealing with ions. They're very similar to just inorganic ions. And so then it becomes really, really hard. But let's sort of talk about the sort of intermediate level problem here. And so just jumping to the solution here, the easiest solution to bind very sort of short chain PFAS is actually use the principle of fluorophilicity, so sort of likes prefers like. And the idea here is you have your copolymer that originally was a sort of two units, and now you can make a terpolymer. So you have a unit that regulates affinity towards a carboxylic group. You have the tempo unit that regulates electrostatics, but now you add a fluorophilic group that in some ways you can recognize it looks like it is a PFAS, that you actually bind to your matrix, and that actually gives you affinity in terms of fluorophilicity. And so with these three polymers, you actually have a combinatorial space that you have to explore in terms of seeing which adsorbent is better for the shorter chain PFAS. And so my student Anira actually led a synthesis of 12 different copolymer adsorbents and then tested for 3 or 4 different types of short chain PFAS. And I'm actually going to just give a little bit the punchline here is, so we tried the C4, the PFBA, and then the C6, which is the PFXA, and both are categorized by the EPA as being short chain PFAS. But we have to say that they have very different properties when in contact with the electrosorbent. So having fluorination in your copolymer adsorbent does not make a big impact on the C6 polymer. And so having just the original amine adsorbent that we use for PFOA works equally well for C6 PFAS. But when you go down to C4 PFAS, the much shorter ones, then the fluorination in your electrosorbent actually plays a big role. And the reason for that is actually sort of fascinating. It's a fundamental physicochemical phenomena, is that everybody, like not everybody, but most people, when they think about fluorophilicity and Teflons and PFAS, they sort of tend to think of it as being hydrophobic. And so hydrophobicity and fluorophilicity are similar under certain conditions. When you go to very short amounts of fluorination, fluorophilicity and hydrophobicity sort of differ. So something can be non-hydrophobic for fluorophilic, and that's actually what's sort of happening with the C4 PFAS here, is that the fluorophilic group has dispersion interactions. They're not classic hydrophobic interactions. And so these are actually captured by MD simulations, which are actually quite accurate in terms of predicting PFAS behavior, just because of the force fields that the chemists have developed for fluorine. And so what I'm trying to say here is that fluorination plays a big role the shorter you become in terms of your PFAS chain length. And so the role of electrical field, so we're doing electrochemistry. Why do we need the electrical field? Especially as you go shorter, it becomes more charge dense. So your kinetics for binding short chain PFAS and adsorption are a lot faster than longer chains. So you can actually have very fast binding of PFAS at 0.9 volts of the C4 PFAS as you're applying an electrical field. And you can also regenerate it very efficiently now for both C4 and C6 because you're not as hydrophobic as the longer chain. And so I guess my punchline here is for short chain PFAS, and the shorter you get, the more electrochemistry plays an impact in terms of adsorption and desorption with lower energy consumption. And so I think one of our reviewers is actually somebody that was very familiar with environmental samples, and they asked us to actually get wastewater samples and then see if we can actually remove PFAS. And so from 10 ppb, we're able to remove quite a little bit. And then if you scale it up, you can remove over like 95%. So it's a question of systems engineering on the size of the systems. One thing that we also had difficulties was the wastewater itself that we collected actually had PFAS in them. And so it's very hard to get in very low concentrations. And we actually ran into trouble with the wastewater plant for telling them that they had PFAS. And so we switched partners there, and then we never tell them what they have in there. And that was a lesson that I learned working with these guys. And so I want to sort of go back to the, to actually show everybody why is it important to up concentrate. And so the overall goal of the PFAS treatment is you have contaminated water and you end up with clean water. And so your first, your first reaction could be, why don't you put a remediation reactive step directly there so you're destroying the PFAS, getting clean water, and then removing it. And the reason for why, in general, we think of systems as separation and reactions is that there is a mass transfer limitation to the reaction if you use it directly for the wastewater or the water. And that, I think that most of us sort of understand that intuitively, but when you see the impact of it, it's actually very clear. So it's actually exponential. So as you improve by an order of magnitude the PFAS concentration, you decrease significantly the energy consumption. And so we're here on the right-hand side doing a quick test case where we basically bind and degrade PFAS directly in the incoming concentration. And you can see that most of the energy now comes from the degradation using the BDD. But then if you just up concentrate your PFOA 5 times, you can decrease your BDD energy consumption by an order of magnitude. So this is a classic case in which you have the reaction, but then that's limiting, and then you use separation, and then you reduce that energy consumption. And then again, going back, like how you do that separation, how you do that reaction, it can be anything. It could be, maybe biologically transformed. The separation could be chemically done, not electrochemically, but the overall principle of it remains that you have to deal with concentrations that basically reduce the overall cost of the system. And so, I guess my talk here, I was sort of invited to give a little bit of overview in terms of electrochemical systems, electrochemical separations. We wrote this review, actually, I guess I forgot to put in the citation, but this is in Chemical Reviews last year that we made this comprehensive sort of overview of the literature. And over the past couple of years, the sort of publications and interest in electrochemical methods has grown up exponentially. Both in terms of the sort of oxidative destruction type techniques, also in terms of separations, whether it's electrodialysis, adsorption, extraction, electrochemically sort of driven technologies have received a lot of interest, not only in water, but also in critical elements and other types of processes. And so the big question is, what is sort of its impact in industrial translation and deployment? And so it's a little bit like many of the membrane separations. You can do a lot of research in it, but can they actually be useful in industry? And so this was something that I sort of prepared for a Gordon conference, and this was like 2 years ago, so there's many other examples. But there's a lot of companies that actually have scaled up electrochemical systems. Whether it's electrodeionization, electrodialysis of bioprocessing, rare earth element removal, or even CO2 capture. There's a lot of companies out there that are commercializing it. And then if you go to some like traditional technologies like the chemical industry or the mining industry, like 3M's electrochemical fluorination, copper deposition, they're done at a very large scale. So the scalability of these technologies there is really, can we actually work in terms of implementing them for water technologies? And so what are our, my group's interests going forward, and a little bit where we're focused on. And so one of the big current topics that combine the chemical manufacturing and the water treatment is actually semiconductors. So we're trying to bring semiconductor manufacturing onto US soil, but then now there's all these EPA regulations. It's a hazardous material. And so you're sort of caught in this between a rock and a hard place. And so to actually substitute PFAS use in semiconductor manufacturing is going to take decades. And for the immediate case, there is a big need by the semiconductor manufacturing to find ways to adapt some of our technologies for their application. And so that's something that we're currently working with the NSF to do. And then there's an upcoming workshop that myself and my co-organizer actually putting together with NSF and Intel on actually looking at PFAS for semiconductor manufacturing streams. And that's something that I think will help guide a little bit the priorities in this area as well. So we're sort of thinking that will be one area in which we can work synergistically with the chemical industry. And so just an overview and conclusions is, I'd like to say, if you know, we showed a lot of data, a lot of systems, but the punchline here is actually very sort of high level, is overcoming mass transfer barriers actually critical for PFAS decontamination, especially because they're low concentration contaminants. And then separations and reactions coupling is one of these things where we talk a lot about, but in PFAS, it's actually something that is actually critical. For complex PFAS pollutants, you know, for the wide variety of the thousands of PFAS that are out there, you often don't have one solution or one polymer, one sorbent. You often have to control many things at the same time. And what I've shown is basically copolymer design is one way that we can actually go about it. And then electrochemistry is a potential candidate for doing energy efficient pathways, but you have to compare electrochemical systems with other systems, sort of apples to apples, when you're kinetically limited, not when you're mass transfer limited. And so with that, I just want to sort of thank my students and collaborators, and then the sort of main funding sources here, which has been really NSF and 3M, and then some funding from other sources in terms of its in terms of giving us some platform technologies. Thank you.